for systems of equations, what we mean by that is basically it's a set of two or more equations. For example, x plus 2y equals 14, and that's going to go with 2x minus 3y equals negative 7. And so that's really all we mean by a system. There are two or more related equations. And so, as far as solutions go, most of these are going to share at least one solution. And so by that, what do I mean? What do I mean by solution to a system? Well, if I'm talking an xy system, it's an ordered pair, an x comma y, that does what? What's it got to do? Well, if we're talking about a system, right, a solution is, it's an x comma y. That's going to work in both equations, right? The xy, to be a solution, has to work in both equations. For example, for this system here, 4, 5 is a solution, or is the solution. There's one solution to this one. So 4, 5 is the solution. And how do I know that? Well, I can know that by checking, plug in the x to be 4, the y to be 5 in both equations, and verify that works. Isn't that true? Because if I plug in 4, 5 for x, y in the top equation, that gives me 4 plus 10. Yeah, sure enough, that is 14. If I plug it into the bottom equation, 2 times 4 minus 3 times 5, that equals negative 7, doesn't it? Because that's 8 minus 15, and that does indeed equal negative 7. So that's what we're talking about. And it's not enough, right, to just work in one of them, because what about 0, 7 for this system? Is it a solution? 0, 7? Works in the top one, doesn't it? So it is? If it works in one of them, that's enough? No. It works in the top one, that's true enough, but what about the bottom one? 2 times 0 minus 3 times 7 does not give me negative 7, does it? It gives me negative 21 equals negative 7, so no. Not a solution. So yeah, even though it works in one of them, it's got to work in both of them, because there's lots of pairs that would work in the top one, but not in the bottom one, and vice versa. It has to work in both, though. If it's a system of 2 equations, it has to work in both. If it's a system of 3, it has to work in all 3. But anyway, that's what we mean by a solution. Now, there's 2 different ways we'll talk about. Actually, I guess we could throw in the third one. We'll talk about a third idea too. But two main ways of finding solutions to equations. Let's talk about those real quick, review those real quick. There's a substitution method. If I have 4x minus 3y equals 18, and I have y equals 14 minus 2x. 4x minus 3y equals 18. Y equals 14 minus 2x. We're going to solve this one by substitution. Now, this one is set up very nicely for substitution, because on substitution what I do is I take one of the variables and replace it by an expression. And the second equation just so happens to be very nice here, because this is saying y equals 14 minus 2x. So in other words, 14 minus 2x is the same as y. In other words, it can be replaced, y can be replaced by the 14 minus 2x expression. Well, if I do that, plug that in to the top equation for y, here's what I get. So since that is the same, I can replace wherever I see the y, I can replace it by 14 minus 2x. So if I do that in the top equation, that gives me 4x minus 3. Now that's times y, so it is going to have to be distributed there, the negative 3, equals 18. Now why would I do such a thing? Well, let's look at it. Because if I distribute my minus 3, 4x minus 3 times 14 is minus 42. And then minus 3 times minus 2x is positive 6x equals 18. You see right there that now I can solve for x, can I? I can get an x value out of that. 4x and 6x is 10x, so 10x minus 42 on the left side. Then I add the 42, and 10x equals 60. Divide by 10, I've got x equals 6. Well, come to find out, that is part of the solution anyway. X is 6 is the x value of the solution. And so all I need to finish this out is the y value of the solution. Well, if I plug in now my x to be 6, either one, it doesn't matter. I could plug in x to be 6 here, but a little bit easier in the second one there. Plug in x to be 6 in the second equation. I can determine my y value. 14 minus 12. Yeah. Tells me y equals 2 to go along with the 6 for x. So 6, 2 is my solution. It will work in both, and you can check that pretty quickly if you plug in x to be 6, y to be 2 there. Yeah, 24, that'd be 24 minus 6. 24 minus 6 is 18, and of course it works in the second one too. All right, so that's substitution method. Well, let me mention one more on that. Is that okay? Question or concern? One quick little point on substitution for this one. 3x minus 5y equals 4. 4y minus x equals 1. Let's solve this one also by substitution. Yeah, the thing is on this one, this one's not set up quite as nicely for substitution, but it can be done by substitution. Won't take too much effort. The thing on substitution is you need one of the variables on a side by itself, right? You need something x or y equals and then the expression. Well, neither one of those equations has that. However, equation number 2 here, it won't be too difficult to solve that one for one of the variables, right? Solve it for x. Why wouldn't I, let's just think about why not any of the others? Solve this one for x, why not something else for one of the others? Well, you'll get fractions. If you can, avoid fractions. Just makes everything a little bit easier, and yeah, everything else will give us some fractions. So let's solve equation 2 for x here, and so that's just going to mean you could do it a couple of ways. Basically, if I just switch sides here for the x and the 1, add the x to both sides and subtract 1 from both sides, I get 4y minus 1 equals x, don't I? And so there is our equivalency for x. So I can take and plug it in for x in the other one, can't I? X is 4y minus 1, so plug that in to my other equation for the x. That'll allow me to solve for y here. I distribute the 3. That 3 does have to be multiplied by both, so it'll be 12y minus 3 minus 5y equals 4. Collect your like terms. 7y minus 3 equals 4. But yeah, that's going to work out nicely. Add the 3, divide by 7. Y equals 1. However, we're not done because you do need both an x and a y for a solution. And that is another note here. You can plug it in wherever you want to for y, but if we go to this one, x is 4y minus 1, that'll be the easiest of the bunch. So y is 1, so I know x would be 3. 3, 1? How's that sound? All right. Method number 2. We call it the elimination method. All right, let's start with that one. Let's do this one. Two x plus 3y equals 17. 5x plus 7y equals 29. Okay? All right. So on this elimination method, what it is you're doing here is, like the name suggests, we're trying to eliminate something, and we're trying to eliminate one of the variables. And so the first step is just to choose one of the variables to eliminate. And in this case, I think, looking at the numbers, the x's, let's eliminate the x's here. Here's why. Because what I'm going to do is I'm looking at the coefficients of the x's and of the y's, and I'm looking at least common multiple. I'm trying to think, what least common multiple do those coefficients share? The x's, the least common multiple would be 10. The y's, 21. So that's why I'm choosing the x's, because it just has a little smaller least common multiple. So here's what I want to do. Least common multiple of the x's is 10, so I'm going to eliminate the x's. So I'm going to make them both be 10. However, one I want to make positive 10, and the other negative 10. Because then when I add them together, 10 minus 10 gives me 0, right? So that eliminates them. So how do I make the top one be, the x term anyway, be 10? Well, it would be multiplied by 5, wouldn't it? And as we know, both sides of the equations have to do the same thing, so I'm going to multiply both sides by 5. To make the bottom one be 10, I want to multiply by 2. However, it needs to be negative 10, so I'm going to multiply by negative 2. Multiply both sides by negative 2. And so this gets me, now, my system be 10x plus 15y, 17 times 5, 105. Negative 2 times the bottom equation will be negative 10x minus 14y equals negative 58. And here's what I do next. Is that okay? Do that right? I'm going to add the two equations together now, because now, 10x minus 10x, that's 0. 0x, that's just 0. And then see what happens in the rest. 15y minus 14y, hey, that's really nice, because that's 1y. 105 minus 58 is 47. Oh, 85. Where? 17 times, how did I get 105? I don't know. So I'm doing 15 times 7? I don't know. Okay. I'm just checking, y'all. 85 minus 58. Is that better? 27? And so that, there you go. 1y, don't even have to do anything. That's telling me my y value is 27. However, I'm not quite done because I need an x and a y. So I need to find the x. How do I do that? Well, let's just go and plug in y to be 27. And it doesn't matter either place. Y to be 27 here, y to be 27 there. It looks like it's easier in the top one, doesn't it? So I'm going to do that. Y is 27. To the top, so that's 2x plus 81. Subtract the 81. So I have 2x equals, that'd be negative 64 divided by 2. X is negative 32. I believe that sounds right. Negative 32, comma 27. All right. One other of those, and then we'll get into one other thing here, and then we'll do some a little bit harder ones. Okay. Question or concern on that one? Get everything else right? It is Monday, you know. So. All right. Here's another one for elimination. Two x plus 5y equals 4, and 3x minus 4y equals negative 17. Now this one, kind of a toss-up on whether to use x and y. Let's just think about it though. The x's would be 6, the y's would be 20. However, it might be a little bit nicer on the y's because I don't have to worry about the positive and negative thing. They're already opposite signs on the y's, so I don't have to think about that. So let's eliminate the y's here. It works either way. The LCM, that, like we said, would be 20, so I need to make both of those be 20. One a positive 20, the other a negative 20. So how would I do that? Well, the top equation I would multiply by, again, making the y's be 20, multiply by 4. So I'm going to multiply, let me do it this way. So I'm going to multiply the whole top equation by 4. So that would be 8x plus 20y equals 16. And the bottom one I'm going to make minus 20. It's already got the minus, so all I have to do is multiply both sides by 5, don't I? And so that would be 15x minus 20y equals, oh, there's my 17 times 5 again. It's negative 85, isn't it? All right. And so, adding those together, 8x plus 15x is 23x. 20y minus 20y, that's 0. 16 minus 85, negative 69. Yeah, that's going to work out nicely. Divide by 23. I'm seeing x is negative 3. Well, if x is negative 3, I can just plug it in to be negative 3. 2 times negative 3 plus 5y equals 4. You can find the y. So negative 6 would equal, negative 6 plus 5y would equal 4. Add the 6 and divide by the 5. I get y to be 2. Yeah, so there's our solution. The ordered pair that would work in both. I haven't checked. I didn't check the other one, but it would indeed work in both. Okay? All right, now, let me talk about one other thing. Like I said, then we'll do some more complicated ones. Is that okay? Any question or concern? And what I was going to try to talk to you about here is why are we getting what we're getting as far as the number of solutions. Each one that I've worked so far, I've gotten one solution. Why is that? Or Can we kind of visualize that? So why are we getting one solution on the previous ones? Why is that? Well, let's take a look at another one. Y equals 3x minus 5, and y equals negative 2x plus 10. Well, first of all, let's think about it. How are you going to solve that one if we were told to solve it? Well, we can do it either way, elimination or substitution. I see substitution working pretty well here, don't you? Because I've got y equals, actually both of them are y equals, so it work either way, but can I substitute this for y in the other one? So negative 2x plus 10 equals 3x minus 5. Just solve that out for x. Let's subtract the 3x and subtract 10. Negative 5x equals negative 15. Divide by negative 5. X is 3. The y value then is going to be 3 times 3 minus 5, be 4. 3, 4. So again, one solution. Why is that? Well, let's think about graphing these things. What are the graphs of 3x minus 5 and y equals negative 2x plus 10? What do those look like individually? What would they look like as graphs? Well, individually, these would look a little bit like lines, wouldn't they? Both of these are in y equals mx plus b form, so let's graph those real quick here. On the first one, we've got an m of 3 and a b of negative 5. And so that means slope is 3, y-intercept's negative 5, so it's going to cross the y-axis at negative 5. That's the way I'm getting this. And it's going to slope of 3, rise to run, so that's 3 over 1. So if I rise 3 and run 1, puts me there, so there's my, I know it's a line, so I can say safely it looks pretty much like this. Now the other one I've got slope is negative 2, y-intercept is 10. But its slope is negative 2 over 1, so let's rise negative 2 down 2 and run 1. So that's there. And hey, look at that. Guess what? They cross. Guess where they cross? At 3, 4. Yeah, this happens to be the intersection point there is the solution to the system. Is that by coincidence? I don't think so. Yeah, if you think about it, if we graph whatever the equations are, if I graph them, if I think about the system, I'm looking for the solution is a point that satisfies both equations. Well, when I graph them, that's the only point that satisfies both equations, isn't it? Any other point, like this point, well, it satisfies that line, but it doesn't satisfy the other line. This point satisfies this line, but yeah, the only point that satisfies both equations is the intersection point. And so that's the connection here, why we're getting one solution on the ones that we did previously. If you go back and look at all the other ones, they weren't quite in this form, but they were linear equations. They had x to the first, y to the first equations, and we talked about those a while back, but every one of those are lines. And so the reason we're getting one solution is there's one point of intersection. Okay? Now, think about this one. So graphically speaking, the solutions to systems are the intersection points. What about this one? What about this system? Y equals 2x plus 3 and y equals 2x minus 5. What happens there? Well, if we solve it, It's just like the other one. So if I plug this in for y, I get 2x minus 5 equals 2x plus 3. And notice there, if I get my x's on one side, negative 5 equals 3. Not possible, no solution, right? Well, there's no solution to that equation, therefore there's no solution to the system. Graphically speaking, though, why do I have no solution? Well, look at, we can graph them, but we talked about that too. What about these two lines? What are they? They're parallel, yeah. They don't intersect. This one's 3, rise 2, run 1. This one's minus 5, y-intercept, rise 2, run 1. Yeah, parallel lines. No intersection. So yeah, if you don't have, I mean, the systems don't always have to be parallel, but if there's no intersection point, that's another reason to say there's no solution. Okay?